So what I'm holding here in my hand is a sample box that consists of a bunch of various different functional materials, everything grown in our lab in chambers, vacuum chambers such as this, right? So for example, here is a material, quantum material, a thin film of a quantum material that is grown on a substrate. And this quantum material emulates the behavior of your neuron in your brain, right? So this can be used for neuromorphic architecture as a neuron. Another material that I'm holding here, again, another thin film called a ferroelectric thin film, which is grown on another substrate. This can store information as ones and zeros and can be used in your computer memory. Are you curious to know how to grow these materials and synthesize these materials with an atomic precision so that they go inside your computers or they go inside newer kinds of electronic device architectures? If that's the case, this course is for you. Hello everyone. Welcome to the NPTEL course on Principles of Functional Materials Synthesis. My name is Pavan. I come from the Center for Nanoscience and Engineering. I'm a faculty member here at the Indian Institute of Science. So these functional materials, they come in various forms, various dimensions. 0 dimensions, what are called nanocrystals. 1 dimension, what are called nanowires. 2 dimension, what are called thin films. And more 3 dimensions, what are called bulk crystals. They can be made using various kinds of techniques, some of them involving chemical synthesis routes, some of them involving physical vapor deposition routes, and so on and so forth. But there is a method to madness. So here in this course, we are not going to look at different techniques separately. Rather, we are going to look at the fundamental principles that unite this nice art of material making or material synthesis. This is like cooking in a kitchen. The fundamental principles that govern this cooking or material synthesis are thermodynamics. The ingredients of cooking are factors like temperature, pressure, the rate of flow of gases, the precursors, etc. So all these things are well and nicely built into the framework of thermodynamics. So first we will actually look into what is material thermodynamics and how materials thermodynamics helps us understand whether synthesis of a particular material is possible or not. Thermodynamics only takes us to a certain extent. And this thermodynamics involves understanding chemical reactions, what is called the reaction thermodynamics, understanding phase diagrams, understanding phase transitions. For example, depositing a gold thin film on as an interconnect on your transistors is a matter of changing gold in a vapor state to a solid state. So there is a vapor to solid state phase transition. So understanding phase transitions, understanding chemical reactions, and so on and so forth. All this comes under the gamut of materials thermodynamics. So we will develop initially the language of materials thermodynamics and stop at a stage where we are able to understand whether a particular material is synthesizable under given conditions or not. If it is synthesizable, we move further. If it is not synthesizable, we say thermodynamics says it is not synthesizable, so we will not synthesize it. So thermodynamics takes us up to that extent, and that is going to be the first part of the course. But then we have to say more. We cannot just stop at a point where we say something is possible or not possible. If something is possible, we have to say how it is possible. And this comes under the gamut of material kinetics. And this is where every material has surfaces. Surfaces influence, even if thermodynamics tells me making this material in so and so phase is possible, the surfaces can stop the possibility, or surfaces can enhance the possibility of making this material. So there is some surface thermodynamics that we should study. So that's going to be the second part of this course. We will start the second part by looking at surfaces. What are surfaces? What is surface energy? How does that go into the bulk thermodynamics, the bulk free energy, and so on and so forth. Then we look at stresses and strains. There are classes of materials which are just single crystalline materials grown at atomic layer by atomic layer in what is called an epitaxial growth. Now, there is a huge amount of elasticity, that is the strain that comes from the substrate or the stresses that come from the substrate or the stresses in the film themselves that play a role in how these materials grow. They are going to add on to the G's, to the free energies that you have calculated using bulk thermodynamics. So that will influence how your material is growing, what is going to be the shape of this material, what is going to be the mode of growth of this material, and so on and so forth. So we look at the elasticity problem, following which we are now in a stage to say, all right, so if a new material is growing, or a new phase is growing from a vapor phase, or a solid phase is growing from a vapor phase, how does this process happen? This happens through what is called nucleation and growth. So what are the various ways in which materials nucleate and then later grow? What are the various models that describe nucleation and growth of materials across various processes? It doesn't matter. This is going to be very process agnostic. So that and then we understand the rate of growth of materials, not just that the material is it is possible to grow the material, but also how fast can we grow the material, and so what are the advantages of growing it fast or growing it slow in terms of how these new phases are nucleating and growing. So we will look at some involved materials theories that explain nucleation and growth, taking into consideration bulk thermodynamics, surface elasticity, and so on and so forth. But then, just telling you about the principles is, I know it's going to make the course boring. So wherever possible, we are going to look at case studies and then try to understand how the principles of thermodynamics and kinetics that we studied are employable in these real life case studies. For example, how do we make single crystals of silicon? How do we make silicon wafers through what is called the Czochralski method? That is a case study that we will do. How do you make nanowires of single crystalline nanowires using what is called a vapor liquid solid process? That is an example, that is a case study that we will do. How do you grow thin films in a layer by layer fashion, in an atomic layer by atomic layer fashion on a substrate? That is a case study we will do. In what modes are thin films not growing in an atomic layer by layer fashion, especially the thin film technology, in what is called a thin film technology? That is something that we are going to look at. How do you just grow one monolayer of some organic material, or one monolayer of a two-dimensional material? That is a case study that we are going to do. And we are going to see that all the principles that we have studied is going to help us design this material synthesis parameter space, and eventually to be able to get the outcome that we desire. So this course in that way is going to help you experimentally first design the material synthesis and then go and do it in your labs. So I invite you to join me in this journey of exploring how to synthesize various functional materials, the physical principles behind that. And for that, please enroll in this NPTEL course. Thank you.